Hello everyone. I am grateful for the opportunity to present our paper, An End-to-End Topic-Enhanced Self-Attention Network for Social Emotion Classification. My name is Chang Wang. I am from Huazhong University of Science and Technology. The work of this paper was completed by me and my supervisor, Professor Wang. It is about sentiment analysis. My presentation will cover the following aspects: the background of our research, the method, the experiments, and the conclusion. First, let me describe the background of the task. The aim of social emotion classification is to predict the distribution of different emotions evoked by an article among its readers. Nowadays, some news websites allow people to vote for emotions after reading a news article. The following picture presents an example of emotion votes for people to express their emotions after reading an article. We can see that 243 people feel amused and some people feel touched. Through normalizing the votes, we can obtain the reader emotion distribution. With the rapid development of web, online reader responses have become more and more important to the spread and the popularity of an article. Therefore, how to automatically predict social emotions has become very important for analyzing public opinions or news recommendation. Existing work on social emotion classification can be roughly divided into three categories: word-based, topic-based, and neural network-based methods. Word-based methods exploit the emotion features at the word level to model word-emotion relations straightforwardly. For example, we can score the emotions of text by using an emotion dictionary. Topic-based methods try to discover associations between topics and emotions by constructing a latent topic model with emotion layer, such as adding an emotion layer into the LDA topic model. Later on, some neural network-based methods based on CNN or STM have been proposed. They can extract semantic information and learn a vector representation for the document. Existing studies have included that both document semantics and topic information can help improve emotion classification. So recently, hybrid methods have been proposed. They try to exploit semantic and topic information simultaneously. Usually, the framework is as follows. There is a neural network to learn a semantic vector and a pre-trained topic model such as LDA to extract the topic vector. Then a fusion network is used to combine the semantic vector and the topic vector for the final emotion prediction. Although these methods can achieve the best results on social emotion classification, the topic inference and the emotion prediction in them are separate because of the pre-training of topic model. That's to say, the topic inference and the emotion prediction cannot be mutually promoted. The contributions of our paper are as follows. First, it is an end-to-end framework. We propose an end-to-end topic-enhanced self-attention network, TESAN, that can jointly perform topic modeling and semantics encoding. Specifically, it contains a neural topic model rather than the traditional LDA, because NTM is easy to be combined with other neural networks. So we design a novel NTM to extract topic information. Then we propose a topic-enhanced self-attention mechanism to encode semantics and fuse it with topic information. Finally, we use a fusion gate to compose the final document representation by integrating the document vector and the document topic embedding. This is the whole framework of TESAN. The left part is the NTM for topic modeling. The right part is the topic-enhanced self-attention mechanism for encoding semantics and generating the topic-enhanced document vector BD. Finally, it is the fusion gate that composes the document representation for emotion classification. Now, we describe our proposed model TESAN in detail. The first component of TESAN is the neurotopic model. NTM is a VAE-like structure, and it infers topics with neural networks. The right part is its structure, including an encoder and a decoder. The encoder of our NTM is the same as PROD LDA, proposed in ICAR 2017. The input is the back-of-word BOW representation. Then a multilayer perceptron with two hidden layers are used to transform X-bow into a hidden vector pi. And then two fully connected layers are used to estimate the mean vector mu0 and the covariance vector sigma0. Based on mu0 and sigma0, we used the reparameterization trick to obtain the latent vector z. So the topic distribution theta equals to softmax z. The decoder of our NTM includes a topic embedding TE layer and a topical word embedding TWE layer. The TE layer is to transform theta into the topic embedding representation VT. The TWE layer is to reconstruct the BOW vector. The goal of the NTM is maximizing the evidence lower bound able. The second component of TESAN is the topic-enhanced self-attention mechanism. It is used to simultaneously encode semantic and topic information into the document vector. First, there is a self-attention layer. This layer is to transform word embedding and position embedding into the context-aware vector. The input X is word embedding plus its position embedding into in our experiments. The position embedding is randomly initiated. Then we use the following functions to calculate the attention scores. For each word, we calculate the attention scores between it and all the words in the input document. Based on the attention weights, we can calculate the context-aware vector z, and the vector z contains the contextual semantic feature of each word. After this layer, we propose a topical attention layer that incorporates the topic information learned by NTM into the document vector BD. The input includes the context-aware vector z from the self-attention layer and the document topic embedding VT from NTM. First, we transform the VT into the hidden state HT. Next, when we calculate the attention scores, we want to measure the similarity between VT and each ZI. So we use the following function to get the attention scores. If a word contains more important topic information, it would obtain higher attention weight AI. Therefore, we can say that VD, the output of the topical attention layer, contains both semantic and topic information. The last component of TESAN is the fusion gate. This layer is used to further enhance the topic information in the final document representation. The input is the document vector VD and the document topic embedding VT. The fusion gate can automatically learn the importance weights of semantic feature and topic feature. We first calculate the gate vector G, then obtain the final document representation VF. After this layer, the VF is fed into the classifier for emotion prediction. The loss function of the whole TESAN includes two terms. The first term is the loss of NTM. Loss NTM equals to minus elbow. The second term is the loss of classification. It is the KL divergence loss between the predicted emotion distribution and the ground truth. Because the loss of NTM is too larger, so we use a hyperparameter lambda to balance loss NTM and loss classification. The whole NTM, the whole TESAN is trained in an end-to-end manner. In this part, we report our experimental results. We conduct experiments on 3 public datasets. The first one is the Xinjiang News dataset. It contains about 5,000 Chinese news articles. These articles are collected from the Chinese news portal Xinjiang.com. There are 6 different emotions. The second one is the Samuel dataset. It is the dataset in Samuel 2007, task 14, and it contains about 1,000 English news headlines. There are 6 different emotions. The third one is the ISEAR dataset. It contains more than 7,000 English paragraphs with 7 different emotions. The details about these 3 datasets are summarized in the right figure. We adopt 2 evaluation metrics, ACC at 1 and AP. ACC at 1 denotes the accuracy of the top-ranked emotion. It can indicate the classification performance of our model. AP means the average Pearson correlation. It can indicate the performance of distribution learning. This table shows our results of ACC at 1 and AP. Our proposed model achieves the best results. For example, gated DRGT is the best existing model for social emotion classification. Compared with it, our TESAN improves ACC at 1 by 2.54%, AP by 3% on the Xinjiang News dataset. There are also some other interesting observations. ETM is a topic-based model. SWAT is a word feature-based model. We can see that ETM achieves much better results in most cases, which indicates that topic information can help improve classification performance. Furthermore, we can also compare the traditional topic model LDA with the proposed neural topic model NTM. The large improvements made by MLP plus NTM show that neural topic model learns more effective topical information than traditional LDA. And then ATT-BISTM means BISTM with attention. SAN means the self-attention network. These 2 models are both semantic encoding networks. They haven't considered topic information, but they still achieve competitive results. It indicates that semantics is also very important for social emotion classification. When comparing ATT-BISTM with SAN. We observe that SAN performs better, which reveals self-attention can capture more effective semantic information than BISTM with attention, even though self-attention has a much simpler architecture and fewer parameters. We also conduct ablation study to verify the effectiveness of topical attention layer and the fusion gate. In TESAN without TA, we replace the topical attention layer with the standard MLP-based attention. In the comparison of TESAN and TESAN without TA, we observe that ACC@1 and AP decrease on the 3 datasets. It reveals the topical attention layer is effective. In the comparison of TESAN and TESAN without gate, we can see that ACC@1 and AP decrease without the fusion gate. It reveals that the fusion gate is also useful in our task. In this part, we analyze time consumption for TESAN and several strong baseline models. We conduct experiments on CNN news. This table shows that our TESAN is with very fast training speed and few parameters. It is about 38 times faster than the best existing model, gated DRGT. Compared with the widely used model, ATT-BISTM, it contains about half of model parameters and a smaller computation time. It is also interesting to find out whether jointly performing topic inference and classification can help improve the quality of topics learned by topic model. For the English dataset, Samuel and ISEAR, we use topic coherence to evaluate the quality of topics. The results are shown in the right table. We can see that the TESAN improves topic coherence by large margins on both datasets. The reason may be that under the guidance of a classification task, the topic model is supervised to produce more meaningful topics. It can also be seen that the prod LDA and NTM perform better than LDA, which implies the effectiveness of neural network-based topic models. For the Chinese dataset, CNN News, we sample a latent topic about hospital and present the top 10 words in the left table. Terms in blue mean non-topic words. They reflect little topic information, and terms in red mean off-topic words. They are more likely to be representative words of other topics. We can see that the result of LDA contains the most off-topic words, like child, son, and so on. Although there are few off-topic words in the result of prod LDA and NTM, they include several non-topic words, like 张腾 and post. Our TESAN has learned the best topic without non-topic word and with only 2 off-topic words. The TESAN has an important hyperparameter, the number of topics. The figure compares ACC@1 for TESAN, NTM plus MLP, and LDA plus MLP on Samuel and ISEAR. We can find that the performance of NTM plus MLP and LDA plus MLP is both easy to be influenced by the topic numbers, but from the results, the TESAN seems more robust, as its performance varies much slightly against the topic numbers. We use a case study to illustrate the topic-enhanced self-attention mechanism in TESAN. Specifically, we visualize its topical attention layer and compare it with the MLP-based attention layer in SAN. Take the test instance from Samuel as an example. The raw sentence is injured marathon winner leaves hospital. We can see the figure A. SAN predicts a round top-ranked emotion label. This is because there are in total 3 instances, including the word injure or injured, in the training dataset, but they are all correctly trained with the same label, sadness. Without the guidance of external information, it is easy to SAN to generate a large attention weight for injured in the test instance and produce a prediction label of sadness. However, our TESAN has not been misled by injured because the word is not the representative term of topics in the test instance. We can see the figure B. We can find that 3 topics mostly relevant to the test instance are the topic 3, 11, and 13. In the word distribution of these 3 topics, marathon and winner has greater probabilities than the other words in the test instance, like injured. This means that marathon and winner are closer to the documented topics, while injured is not much relevant. Therefore, the topical attention layer of TESAN assigns larger weights to marathon and winner, and the weight of injured is suppressed to a smaller value, as is visualized in figure D. As a result, for marathon winner being always associated with a positive emotion in the training dataset, our TESAN can correctly predict the top-ranked emotion as joy. Finally, I would like to make a conclusion for my presentation. In our paper, we have proposed an end-to-end topic-enhanced self-attention network (TESAN) for social emotion classification. The TESAN contains a neural topic model for topic modeling, a topic-enhanced self-attention mechanism for encoding semantics and topic information, a fusion gate to compose the final document representation. In the future, we would like to study how to further exploit other features, such as syntactic knowledge for social emotion classification. Okay, that's everything about my presentation. Thank you very much for your kind attention. If you have any questions, please email me. The email addresses are on the slide. Thank you.